Hello, juniors. This is Mr. Reynolds looking at our second lesson and talking about cosmology, taking a look at the universe, trying to understand how the universe was started and how the universe has changed and what's happening with the universe now. And I know it's sort of mind-blowing a little bit, but stick with me. The universe is expanding. Everywhere we look, things are moving away from us. And the farther you are away, the faster they're moving away. Inside our galaxy, we don't see things moving away from us. We're talking about very distant galaxies. We're talking about things in millions of parsecs. Okay, hundreds of millions of parsecs. These are very distant objects. Now, some people might ask, Mr. Reynolds, how big is the universe? Because the universe is not necessarily a room. It's not like the stars are racing to fill up the room. The universe is probably a certain size, we think. It could be infinite, but probably infinite's a sort of tough thing for scientists to wrap their brain around sometimes. The problem is the universe is about 14 billion years old. Now, the only way we can see things is we can see things that have been traveling for 14 billion years. Because that's how long light has had to travel. So if you're too far away, well, light hasn't had a chance to get to us yet. And so there's a lot in the universe we can't see. Now, everywhere we look, things look pretty much the same, which tells us, well, we're probably not at the edge of the universe. We're probably not like on the outer realm there because, if we looked one direction and saw nothing, well, okay, maybe we're on the edge somewhere. Maybe a really bright area. That'd be the center of the universe. And we don't see that. So we're not really quite sure on that one. So today I want to take a look at this idea that the universe is expanding and that more distant galaxies are moving away faster. And to do this, we're going to take on the work of a guy named Edwin Hubble. This is a scientist who made a graph, very important graph. He studied very, very distant galaxies. He was able to measure very distant galaxies by looking at these things called Type 1a supernovas. These are supernovas that are very distinctive. We know when a Type 1a supernova has happened, and they always give off the same amount of power. We know the luminosity of a Type 1a supernova. Well, if you know the luminosity, you can use the brightness equation to figure out the distance to an object, and that's what we do. So we use this measurement of using these Type 1a supernovas to measure the distance. And we measure it in megaparsecs. Now, mega means a million. These are huge distances. And guys, this is not a measurement that we have down perfectly. Okay, there's a lot of unknowns here. Scientists don't agree on all of this because it's so darn tough. We're talking uncertainties of like 100 million parsecs of uncertainty to the distance of things. But, for our purposes, it's going to work. The other thing we can tell by looking at these distant galaxies is we can tell the recession velocity. We talked about that in the last chapter. We talked about the fact that using the redshift equations, we can measure the recession velocity pretty well. Now, for whatever reason, astrophysicists like to use kilometers per second as the recession velocity unit. So he made measurements of many distant galaxies, and for the most part, they tended to form a nice pattern. And they made a nice little line that looked like this. And what he did is he said, he drew line. Whoops. Well, let's imagine that was let's try to draw a little better of a straight line here. There we go. And he drew a nice little straight line. And he said, we're going to take the slope of that line. We're going to call that h0. Now, h0 is known as Hubble's constant. Very important number. The slope of that line is Hubble's constant, very important number. And it's a number that is not totally agreed upon. This is not something where we know Hubble's constant to the nearest, the nearest decimal or the 100th decimal point or the 10,000th decimal point or whatever. Okay? We know that, Hubble's constant maybe anywhere from 60 megapars. maybe about 60 kilometer megaparsec seconds to about 90 kilometers megaparsec seconds. A huge range. Okay, huge range. And the reason we don't know it very well is it's really hard to tell how far away these things are. There's a big, big uncertainty when you're looking at these very distant objects. It's something scientists are working on right now. Another thing that this Hubble's law relies upon is a constant rate of expansion. And you're going to find out how in next chapter we're going to talk about why that may not be the best idea, but it's the best we got right now. And so what he's done is he made an equation, said the recession velocity is equal to Hubble's constant multiplied by the distance. Now, you may be asking, Mr. Reynolds, what do we use as Hubble constant? I turned to the data booklet, I went to the constants page, there was no Hubble's constant. You're right. Because honestly, this is something that changes every year on the test. You will be told what Hubble constant to use. They will tell you a Hubble constant, or you'll need to find a Hubble constant. You might need to find the slope of this graph. Okay? But you will not need to know a particular Hubble's constant. But what this constant shows us is that as the distance to an object gets higher, the recession velocity also gets higher. Now, there is one interesting thing we can do with this. There is one interesting thing that can happen with this equation. And that is looking at this equation. Velocity is distance over time. And one thing that Hubble realized is, well, he had this equation again, so velocity equals h naught times distance. And so what he was able to do is say, well, hold on here. Velocity equals 1 over t times distance. Velocity equals h naught times distance. And so what he did is he said, well, okay, we're going to say that Hubble's constant equals 1 over time. Now, this is a very particular time. Very special time. In fact, the data booklet lists this as big T is about equal to 1 over h naught. Now, this is a very important time because this time is the age of the universe. You can find the age of the universe simply by taking 1 over h naught. You might say, Mr. Reynolds, that seems like a very easy thing to do. Very simple equation you've given us. Well, it is. Not too bad. But it can actually be somewhat tricky. Let's just take a Hubble's constant of, let's just say 70. Now, remember the units of Hubble's constant. Kilometer per second megaparsec. Now, I could go in and say, well, okay, let's use a different color here. Age of the universe equals 1 over 70 kilometer per second megaparsec. Okay, that's easy enough to do. And I could do the math. Let me get my calculator. 1 divided by 70. Okay, that's going to be a 0.014 second megaparsecs over kilometers. Now, we're trying to find the age of the universe. That's not very satisfying, honestly. 0.014 second megaparsecs over kilometers. That's not a unit of time. I want the time in seconds. I want to know to the second how old is the universe. So, I'm not going to do this. What I'm going to do is I'm going to list things out like such. I'm going to write this like this. I'm going to say 1 second megaparsec over 70 kilometers. Now, what you'll notice is I have a time unit. That's good. That's what I want. So seconds are cool. We're going to leave those. I have 2 units of distance, megaparsecs and kilometers. I need to find a way to cancel those out. I need to cancel those two. They're both distance, so it shouldn't be that bad. So we're going to go through a couple things. So for example, first of all, let's get that mega out of there. 1 megaparsec is equivalent to 10 to the 6 parsecs. Megaparsecs cancels out. This is just like dimensional analysis in chemistry. So now I've got parsecs on top of kilometers. Well, I know the parsecs to light years. That's in the data booklet. So I could say, well, okay, 1 parsec in the data booklet on page 2, it'll tell you that 1 parsec is 3.26 light years. Parsecs canceled out. And let's see, light years, well, what could I do? I could turn those into meters. So I could say 1 light year. 1 light year is equivalent to, look at my number here, 9.46 times 10 to the 15th meters. Light years cancels out. We've got meters on top of kilometers. Well, I can get rid of kilometers. So for every 1 kilometer, there are 10 to the 3rd meters. Kilometers cancels out. And all I've got to do to find the age of the universe is multiply everything on top, divide everything on the bottom. And so that's what we're going to do. We're going to multiply everything on top. In fact, I'm going to use pCalc here because I put my calculator down somewhere and I can't find it. So let's see. Let's just multiply everything on top. So I've got 1. Well, that doesn't help. 10 to the 6. Okay. Times 3.26. Times 9.46 times 10 to the 15th. Times 1. Don't worry about that. Divide by 70. And divide by 10 to the 3rd. And I get an answer in sort of a weird format here of, I'll say 4.4 times 10 to the 17th seconds. Well, it's honestly not very satisfying because I'd like it in years. It's sort of tough to tell in seconds. So let's go, let's say there's 3,600 seconds in 1 hour, 24 hours in 1 day, 365.25 days in 1 year. So seconds cancels, hours cancel, days cancel, I'm left with years. So let's see, I'm going to take that value, I'm going to divide by 3,600. I'm going to divide by 24. I'm going to divide by 365.25. And we get an age of the universe equal to 14 times 10 to the 9th years. That is 14 billion years. Now, what do we need to solve for that? Well, you had to have a Hubble's constant. Hubble's constant is something we can get via experimental data. And this is a way of actually solving for the age of the universe from experimental data. Now, you'll notice, there's a squiggly equal sign again. There's a lot of uncertainty going in here. And this is something scientists are still working on and tweaking. This isn't perfect. But on your paper 3 in next year, I would be shocked if they didn't ask you some kind of question. Whether you're HL, SL, I don't care. Hubble's law probably is going to be on there. You see this graph a whole lot. This kind of calculation occurs a whole lot. And again, it's not too tough. You just have to know how to do dimensional analysis. You might even need to use this equation to solve for the recession velocity for a distant star. Okay, so there's a lot of things you could do. You could even take this velocity here, and combine it with the other velocity we found here. Use that in that equation. You can combine these equations, no problem at all. So with that, I want you to do 2 things. I first would like you to watch the second part of the Crash Course Cosmology video, and then I want you to try out some the worksheet. Okay, the worksheet is their IB questions. It goes through and you'll see Hubble's law questions. You'll use redshift equations and all that kind of stuff. So it's a good example of what types of questions you need to answer. I'd like you to take a picture or scan a copy and upload it to ManageBack. Now, guys, we've been having some issues with scanning documents. If you have an iPhone or an iPad, you can use the Notes app, I believe, will even scan a document. Just dive into it. If you have the Dropbox app, it'll scan a document. You can scan multiple pages and combine them into one PDF and just upload that PDF. If you use an Android, I'm sure there's other solutions out there. I'm sure there's free solutions. Just do a little Google search, how to scan papers. This is something you probably do need to know how to do. This is something I do a lot, scanning papers and sending them off other places. So I would encourage you to try to figure out how to do that and then submit it to the assignment that is listed for you. Please come with questions for our Zoom meetings, whether it's going to be on Wednesday or Thursday. I'd love to answer them. This is a topic where I would expect questions. Okay, so please bring them. I'd love to talk about it with you. I may tell you I don't know a whole bunch because maybe scientists don't know. Maybe I don't know. I had a student ask me something the other day. I said, "Well, it's very complicated." He says, "Oh, tell me anyway." I was like, "No, it's really complicated. I don't know." So I'll be happy to tell you I don't know if it's a topic that I just am not so sure about. But please ask because this is some interesting things knowing how the universe works. Hope you all have a good day, and I will catch you later.